Hi, in this lesson we'll consider the equation of the line. Let's try to write down the equation of the line, which passes through the point M0 with coordinates x0, z0, y0, and parallel to the vector S with coordinates m and p. Let's draw our coordinates x, y, z, and let point M0 be here, and vector C, to which our line should be parallel. By the way, this sector C is called the directing vector. Now do the following. Connect the origin to the point M0 and draw a radius vector from this point to M0 and call this vector P0. Now, point M, arbitrary point M with coordinates x, y, z, belongs to our line L in the following case. That is, we need to draw a straight line parallel to S. Let's take some arbitrary point M, which lies on this line. If we find the coordinates of the point M, then we have set the equation of the line. Similarly, draw a radius vector from the origin and call this vector R. Now we express the vector R. Obviously, the vector R is equal to the vector R0 plus vector M0M by the rule of vector addition by the triangle rule. Here the vector R shows the xyz coordinates, so this equation shows all the points that lie on this lane, but since the vector M0M is collinear with the vector C, they are parallel. Then can be expressed as vector S multiplied by some parameter. So we can introduce the equation of the line in the following form. R is equal to R0 plus vector S multiplied by some parameter t. This equation is called the parametric equation of the line, where R0 sets a radius vector drawn to the point M0 with known coordinates m and p, a vector that is parallel to our line. Now the parameter t. We get different points by changing it. So we've got a vector parametric equation of the line. If we write down this vector parametric equation of the line as coordinates, since R, R0, and S are vectors, then we get the following. Let's express the x-coordinate. X-coordinate of the vector R will be x0 plus. X-coordinate of the vector S is m. That is m multiplied by t. Similarly, the y-coordinate, this will be y0 plus n multiplied by t. And the z-coordinate is z0 plus p multiplied by t. Now we have the equation of the line in this form. This equation of the line is essentially a written version of a vector equation. This equation is called the parametric equation of the line. If we express this parameter t in this parametric equation, then we get the following. From the first we get the parameter t is x minus x0 divided by m. From the second we get that t is y minus y0 divided by n. And from the third we get z minus z0 divided by p. Now if you have parameter t everywhere, then we can equate the right parts. As a result we get x minus x0 divided by m is equal to y minus y0 divided by n is equal to z minus z0 divided by p. We have a new equation of the line which is called the canonical equation. This is the canonical equation of the line. Here we have x0, y0, z0. This is the point through which our line passes, and the vector with coordinates m and p is the direction vector. Now, knowing the canonical equation of the line, we can easily draw up the equation of the line, which passes through 2 points. Let's have 2 points. A with coordinates x1, y1, z1, and B with coordinates x2, y2, z2. And let's try to draw up a canonical equation of the line. For this we can take any of them as a point x0, y0, z0. For example, point A. Then we get x minus x1, y minus 1, z minus z1, As we have said, coordinates of the direction vector should be below. In this case, the vector AB can be taken as the direction vector. Accordingly, the coordinates of the vector AB will be the coordinates of the direction vector. We can find the coordinates of the vector AB very easily. We subtract the coordinates of the beginning from the coordinates of the end. By the way, we could take BA. This is the same thing. So, AB has coordinates x2 minus x1. So we have x2 minus x1 instead of m. Here we will have y2 minus y1, z2 minus z1. So we have drawn up the equation of the line that passes through 2 points. Thus, knowing any of these equations, we can easily get all the other equations. For example, if we know the canonical equation of the line, then in order to get a parametric one from it, we equate everything to the parameter t and express x, y, z, and after this we get the parametric equation. If you know the parametric, then you can easily draw up a vector parametric. Or if you know 2 points, then you can easily formulate the equation of the line. Let's consider one more kind of drawing up the equation of the line. We remember that 2 planes intersect in a straight line in space. Thus we can set some line as the intersection of 2 planes. So let's have 2 planes, A1x, B1y, C1z plus D1 is equal to 0. And the second plane, A2x plus B2y plus C2z plus D2 is equal to 0. So if these 2 planes are not parallel, they will not be parallel when the normals to these planes are not collinear. Let me remind you that the normal of the first plane is a vector with coordinates A1, B1, C1. The normal of the second plane is a vector with coordinates A2, B2, C2. So if these planes are not parallel, that is, the normals are not collinear, which means n1 is not collinear to n2, then these planes intersect, and they draw up some line at the intersection. Such drawing up of the line is called the general equation of the line. Then we can calculate the direction vector of this line, S, as the vector product of vectors n1 and n2. Thus, if we have 2 planes, then we can calculate a directing line. And we need some point. We need to take some point M0 with coordinates x0, y0, z0. We choose this point as a solution to this system. Any solution being substituted into this system gives us the correct equation. Let's consider an example. Let's have the general equation of the line, and we need to draw up, let's say, the canonical equation. So we write the normal to the first plane. N1 will be a vector with coordinates 1, minus 1, 2. And we write the normal to the second plane. It's a vector with coordinates 3, 1, minus 5. Knowing the normals using this formula, we can find the direction vector S. That is, S is like a vector product of n1 and n2 vectors. Let me remind you that we can calculate the vector product as a determinant. In the first line, we have vectors I, j, k. Then there are the coordinates of the first vector, 1, minus 1, 2, and the coordinates of the second vector, 3, 1, minus 5. As a result, we get some vector with the following coordinates. The x-coordinate is calculated as follows. Expand this determinant along the first line, and the coefficient in front of I will give us the x-coordinate. So we find the algebraic complement for this element. That is, we cross out the first row, the first column. This determinant remains. We consider this determinant, it is equal to 3. So the x-coordinate is 3. Then we find y-coordinate. That is, we find the algebraic complement to j. We cross out the first line, the second column. This determinant remains 1, 3, minus 5. Calculated, it is minus 5, minus 6, minus 11. But we take into account that this is the first row, and the second column, that is 1 plus 2, is equal to 3, and minus 1 to the power of 3 is minus 1. We need to change the sign. We got 11 in total, so here is just 11. And then we find the complement to the k vector. It is this determinant. 1 minus 1, 3, 1. Calculating, it is 4. As a result, we've got a vector with coordinates 3, 11, 4. This is the directing vector of our line. Now we need to find some solution to this system. That is, we need to find a point M0. The easiest way to do this is the following. Since we have 3 unknowns and 2 equations, the solution is infinite. Thus, we can take any number as z, for example. It is convenient to take 0 as z. If z is equal to 0, then we get the following system. X minus y is equal to, and we move 4 here, minus 4. Here we get 3x plus y is equal to 8. It remains to find x and y. They are easy to find. If we add them, then we get 4x is equal to 4. So x is equal to 1. If x is equal to 1, then y is equal to 5. Thus, a point with coordinates 1, 5, and 0 is a point that belongs to our line. So we know the point. We know the direction vector, so we can easily form the canonical equation. The canonical will be x minus point coordinates 1 and divided by the vector coordinates 3 is equal to y minus 5 divided by 11 is equal to z minus 0 divided by 4. We have drawn up the canonical equation of the line. If we want to form a parametric, then we equate everything to some parameter t, and from here we can express x, y, and z. Let's consider the equation of the mutual arrangement of 2 lines in space. Let's consider the equation of 2 lines, L1 and L2, given, let's say, in canonical form. That is the first equation, x minus x1 by m1, y minus y1 by n1, z minus z1 by p1. And the second equation, x minus x2 by m2, y minus y2 by n2, z minus z2 by p2. So we have 2 equations and we need to identify their mutual arrangement. Let me remind you that lines can be parallel in space, or intersect, or be crossed. In order to determine their mutual arrangement, we need to find the direction vectors. The direction vector of the first line is the vector with coordinates m1, n1, p1. The direction vector of the second line is the vector with coordinates m2, n2, p2. Also, the first line passes through the point m1 with coordinates x1, y1, z1. The second one passes through the point m2 with coordinates x2, y2, z2. So lines L1 and L2 intersect in space. I'll write it like this. L1 intersects L2 if and only if the mixed product of vectors m1, m2 by s1, s2 is equal to 0. Let me remind you how we can find the mixed product. We need to find the cross product of the first 2 vectors, and then we multiply the result by the second vector scalarly. Or we can multiply the next 2 vectors first, and then multiply the result by the first vector scalarly. So, if this mixed product is equal to 0, then these lines L1 and L2 intersect. Now, the second possible arrangement when the lines L1 and L2 are parallel. Now, the second possible arrangement when the lines L1 and L2 are parallel. Let me remind you that parallel lines are lines that don't have common points and lie in the same plane. So these lines will be parallel. Firstly, when the direction vectors are collinear. S1 is collinear to S2. But on the other hand, these 2 vectors should be not collinear to the vectors m1 and m2. Let me explain this. Let's have 2 parallel lines. This vector has directions s1, this s2, and you can see that they are collinear. Now let's take point m1 here, point m2 here, through which these lines pass. And it is clear that the vectors s1 and s2 are not collinear to m1 and m2, but the lines are parallel. Thus, this sets the condition of parallelism. But what will happen if vectors s1 will be collinear to s2? And at the same time, it will be collinear to m1, m2. This is possible only in the case when the lines fully coincide. In other words, it is the same line. Indeed, for example, our line, here is the vector S1, somewhere here is the vector, let's say, S2. Point M1, point M2. If we took a closer look at all of these vectors, then we'll see that they are collinear to each other, because they lie on one line. That is, these lines L1 and L2 will coincide in this case. Thus, according to these three conditions, we can determine the mutual arrangement of two lines in space. Let's consider the question of finding the distance from a point to a line. Let's suppose we have some line that passes through the point M0 with coordinates x0, y0, s0 and has a direction vector s, coordinates m and p. And let's have some point M1 here. We need to calculate the distance from point M1 to line L. In order to find the distance, we should drop a perpendicular from this point. And let's denote this perpendicular as h. What is h equal to? It turns out that we can calculate the distance from a point to a line as follows. We have to make a scalar product, vector m1, to multiply m1, m0 by s. Find the length of this vector and divide it by the length of the vector s. Let me explain this. m1, m0. Connect this vector. Find the direction vector s. Mark it on the line itself. Something like this. And we know that if we do a vector product of m1, one vector by another, then numerically it is equal to the area of the parallelogram, which is built on these two vectors. That is, in fact, this value shows the area of this parallelogram. But if we divide the area of this parallelogram by one of its sides, then we get the height. Because the area of a parallelogram, let me remind you, is equal to the height times the side. From here we can calculate the height. The area divided by the side. Same here. We divide the area of the parallelogram by its side, and thus we can find the distance from a given point to a given line. Now, let's consider the question of the mutual arrangement of the plane and the line. Let's have some plane alpha by the equation ax plus by plus cz plus d is equal to 0. And we have some line L in the parametric form. That is, x is x0 plus mt, y is y0 plus nt, z is z0 plus pt. If we have a different kind of equation, then we can always reduce it to a parametric form. Now, in order to set the mutual arrangement of this plane and this line, these x, y, and z, that is x0 plus mt, y0 plus nt, and so on, are substituted into the plane equation. Substitute in the equation of the plane, group the terms with t. As a result, we get terms with t will be equal to am plus bn plus cp multiplied by t. And we group all the other terms. It will be ax0, by0, cz0, and d. And it is equal to 0. We've got the following equation for t. Let's denote this. The whole bracket as, let's say, m for convenience, and this bracket as n. Now, depending on the value of m and n, we could have different mutual arrangements of the line and the plane. Let's consider the first case, when the number m is not equal to 0. If the number m is not equal to 0, then we can express t as an explicit form from here as n divided by minus m. That is, there will be minus n divided by m. That is, we can explicitly calculate t from this equation. If we can calculate t, then we'll find the point x, y, and z by substituting it here. We have found one single common point to the line and the plane, which means that the line and the plane intersect in this case. That is, the plane intersects with the line. Let's consider the second case. When the number m is equal to 0 and the number n is not equal to 0. Then we get the following. If m is 0, then everything is 0. N is equal to 0 and remains here. But since according to the condition n is not equal to 0, then the equality is not fulfilled. If equality is not fulfilled, then this equation has no solution. If it has no solution, then we cannot find t. Then this line and this plane have no common points. And if there are no common points, then the line will be parallel to the plane. And the last case. When m is 0 and n is 0, we get the correct equality in this case. 0 is 0. It turns out, whatever t we take, we get the right equality. So this equation has an infinite number of solutions. It will have an infinite number of solutions when this line lies in the plane. That is, the line L is contained in our plane. Thus, in order to determine arrangement between a line and a plane, we must express the equation of a line in a parametric form, substitute it into the equation of a plane, and analyze the resulting equation. Now let's try to find the angle between the plane and the line. Let's suppose we have some plane alpha. Its normal is vector n. Let it intersect some line with direction vector s. The line is parallel to the plane, then the angle between them is considered equal to 0. Now, to find the angle between the line and the plane, that is, in fact, we need to find this angle, phi. First of all, we'll find this angle between the vectors n and s. Angle cosine alpha can be found very easily by the scalar product formula. Namely, the cosine is equal to the scalar product divided by the product of their lengths. Now, what we found the alpha angle. It is obvious that the angle alpha and phi are connected through pi in half. Thus, if we know the cosine, then we can calculate the sine of phi. But we can have a negative cosine as well, but phi angle here will be from 0 to 90. Therefore, we can take the modulus of this cosine to calculate the sine of phi. Thus, we get that the sine of the angle between the plane and the line will be the modulus of the scalar product of the normal and the direction vector divided by the product of the lengths of these vectors. Knowing the sine of phi, we can easily find phi. Thus, we can find the angle between the line and the plane. Finally, let's consider an example. Let's have a line L and a plane alpha. Let's try to establish the mutual arrangement of this line and the plane. We need a parametric equation for this, of line L. As I've said, in order to calculate the parametric equation, we simply equate it to the parameter t and express x, y, and z from this. So we get that x is equal to 2 times t. Move 1, get minus 1 plus 2t. Y is equal to 4 times t. Move minus 3 plus 3. There will be 3 plus 4t. And z is equal to 3t. Now, we know the parametric equation of a line. That is, we have expressed x, y, and z. We substitute these values to our plane. We get the following. We group the terms with t, namely 3 times 2, 6 minus 3 times 4, minus 12. 6 minus 12 minus 6. And 2 times 3 is 6. The total is 0. So it is 0 multiplied by t. And let's count the numbers. 3 times minus 1, minus 3. Minus 3 times 3, minus 9. Minus 3 minus 9, minus 12. 2 times 3 is 6. Minus 12 plus 6 is minus 6. And minus 5 is minus 11. Is equal to 0. We've got that we have 0 here. Minus 11 is 0. It is false. That is, minus 11 isn't equal to 0. Thus, this equation has no solution. If this equation has no solution, then we cannot find t. We cannot find the point of intersection. If lines don't have a point of intersection, then these lines, the line and the plane, are parallel. This video lesson is over.